illustrate why previous method of sensitivity analysis fails, let's look at the simplest possible chaotic system, the Lorentz system. The Lorentz system, so this guy is Lorentz, Edward Lorentz. He's a professor at MIT a while ago. And the Lorentz system models the heat-driven convection between a hot surface and a cold surface. It has three variables representing the circulation and the horizontal vertical temperature in equilibrium. Okay, and the Lorentz system is very easy to program. So all of you read MATLAB, right? So this is a MATLAB code for simulating the Lorentz system, and these three lines are the formula of the Lorentz system. And can you tell what integration method I'm using here? Huh? Forward Euler, exactly. Okay, good. I have the right audience. Now this is I took the code, I swept over a range of R. So I fix S and B, I switch over a range of R. R is the Rayleigh number. That is basically a non-dimensional parameter of how much temperature difference do I have between the two plates. And this is the mean of Z that represents how much circulation I get, like time average circulation I get. And it looks like a very smooth function, right? Okay, in Q, you compute the sensitivity. So this function calls the Lorentz int on two different R's. One is 28, one is 28 plus something. So who can tell what method I'm using to compute the derivative?
Finite difference.
It's a special type of finite difference.
Oh, okay. You got the imaginary part in there?
Yes.
Yeah.
Oh,
it's a complex derivative. Yeah, that's right. It's 10 to the minus 60 J, right? And this is what I get. I mean, you can take exactly that MATLAB code and push a button, and you get exactly this number, minus 7.78 times 10 to the plus 43.
So MATLAB I should take it, like 10 to minus 60? I didn't know that.
That's the beauty of the complex derivative. And you can ask Professor Alonso why that can give you a good gradient.
New trick I'm learning.
Okay, good. Yeah, so because MATLAB actually represents this as two numbers.
Oh, so it doesn't matter.
Exactly, so it doesn't matter. There is no cancellation. There is no round-off error. That's the beauty of the complex derivative method. Good. So yeah, so this function that looks very smooth actually has a derivative that is larger than almost anything you can produce using such a short piece of code. So why is that the case? Let's take a look at actually what the Lorentz system does. So you see the dot over here? That is a point in the X and Z space of the Lorentz attractor. Okay, I'm going to start the simulation from that position with a range of different Rayleigh numbers encoded by the color spectrum. So you have red to purple. So different color represent different Rayleigh numbers. So this is a millions of simulations actually I'm performing here. And this is a demonstration of different simulations with a different parameter producing very different states after a while. And even very, very close by parameters, very, very close colors, almost the same color you're going to see is going to become completely different in the phase space. And this not only stretches out, but it falls back and stretches out again, falls back and stretches out again. And that makes the simulation very different, even for very similar parameters. And ultimately, it comes into basically a completely messed up state, right? So this is fundamentally why we can't do sensitivity analysis to chaotic systems. And if you plot the same movie here, but in a static plot, so this is the input parameter, and this is time, and you look at one of the quantity of interest, and you can see as time goes on, there are more and more oscillations, right? I mean, each one of them are a stretch and folding. You stretch and fold, the number of peaks goes as time increases, the number of peaks goes up by what function of time? Exponential, exactly. Okay, so yeah, the number of peaks increases exponentially.
A plus.
Now, also, so this is if you time average this objective function, and this is actually the time average. I forgot to say that is one of the very interesting quantities many engineers are looking for in these chaotic simulations. For example, in the turbine blade case, the time average heat transfer is what people are focused about. So if you look at the time average, a good thing about the time average is that it averages out a lot of peaks. So that instead of seeing wild oscillations from like 0 to 60, you only see a range from 20 to 30. Now, interestingly, the objective function in a chaotic simulation is like a stochastic time series. So when you average out a stochastic time series, what is the rate of convergence? It's like Monte Carlo. What is the rate of convergence of Monte Carlo? Square root of t, right? Okay, so compare what we just said. The number of peaks increases like exponential of t. The size decreases like square root of t. Which one wins? Exponential, right? So that is why when you take a derivative, the derivative increases like exponential of t divided by square root of t. And the exponential of t wins by no comparison, right? So that is why the derivative increases by a huge amount. As you increase the time, these oscillations are going to shrink, but it doesn't help you computing your derivative.